Hi everyone. This is Andy and June and Midu. We're going to give you a quick overview about a project we have been working on called CaffeOnSpark. I think you guys now heard enough of Spark. We thought it's time for it to wake you up, so we put a little coffee on top of it. So that's the main purpose. So for the joke aside, Caffe actually is one very popular deep learning framework. And on the other hand, Spark, as you guys know, is a very popular big data framework. So what we wanted to do here is show you how to bring them together so that you could learn interesting stuff from your data, make some business out of it. Okay, so the way, just sit on this stage. So a team of us, we have been working on the machine learning things, but we are part of our Hadoop team. So what we decided to do is we have expanded our Hadoop clusters beyond the CPU until recently. So we have the GPU nodes inside our Hadoop cluster. And then in that cluster, we run Hadoop, we run Spark, we run Storm, and we also introduce some of our infrastructure called parameter server sources. And then on top of that, we have been working on a set of very large scale machine learning algorithms. And so we have been very basic things like logistics regressions. We do something like the word embeddings or things. But for today's talk, we're going to cover logically is the deep learning side of the story we're going to cover. So the information we're going to share today, most of them is public, and as we announced, it was about 6 weeks back. I think we announced our open source software called CaffeOnSpark. It is available on the GitHub Yahoo CaffeOnSpark. We are just following our tradition of the Hadoop. Remember 10 years ago, Yahoo, we spent all of the energy developing a piece of software called Hadoop. And then we decided to donate it to open source community. Now it's a big deal, right? So we thought, CaffeOnSpark is not such a big piece of the software, but we will follow the same trend. So we made the software available under the Apache 2 license. And in order to make sure it's easy for everybody else to use, we made the CaffeOnSpark available on the CPU in addition to GPU. And inside our company, we use a very fast network called InfiniBand. But I think we realize many of you may only have Ethernet. So we also make the Ethernet available as a connectivity between our nodes. And then today we're going to give a demo that even if you do not have machines, as long as you have a credit card, you could do the deep learning. So we'll show you how you spend money to our dear friend for Amazon, okay? So with that, I think I'm going to get out and have June going to talk to give you a quick overview about what is deep learning, what is the CaffeOnSpark. Then Major is going to teach you how to spend your money with EC2. Thank you.
Hi everybody, my name is June. So I'm going to talk about the topics. Can you go to the next slide? Actually, so how many of you have heard of deep learning? Oh yeah, that's what I expected. So a lot of people. So at 8 o'clock in the evening, I'm not going to talk about too much about deep learning because it's very deep. So I'll just give you, we're going to scratch the surface. Actually, we're not going to scratch the surface. So we just, give a few examples. So the hello world application, usually it's MNIST. So it's handwriting recognition. So basically, this is from the post office probably many years back. They collect a set of these handwritings. And you're trying to let the computer to recognize it. And this problem pretty much solved. So it's you can get like a 99.9 kind of accuracy. So this is one of the early applications. Of course, recently we have we have heard this on the news, right? So actually be the human actually. This person is very good. So that's kind of advance we have made. So deep learning basically it's a nonlinear algorithm. It's a branch of the machine learning. It initially the scientists wanted to mimic the way the human brain works, and that's why they have all these layers. And the more layers you have, the complex the network is, the more powerful the network is. So on the right-hand side, this is I believe the 2014 Google Net. So they use this network they won this ImageNet competition basically. So that's I believe this is about 27 layers. So it's very deep and very powerful. So at Yahoo, we use it. One of them. Well, we have a lot of applications. So this is one of them, the Flickr. So a lot of people probably have experience with this. So we have a new product. Actually, so we have a product called the Camera Row. So if you use that, and you can select the topics, and it automatically pick up the images that fall in that category. So behind the scene, actually, it's running training and it's running the inference. So at Flickr, this is our pipeline. So basically, we first prepare the data. So user uploaded, lots of data. So we prepared. Then we use the Caffe on Spark, which is mentioned, to train the model. Then from the model, we extract the features. And we use that feature to do a non-deep learning. Then we apply the model to the real data set. So that has been the pipeline. So it's built on the Hadoop or the Spark, and we use also use Storm for the serving. So previously, what we did was we have two clusters. One is a deep learning cluster, which mainly consists of GPU nodes. And then we have the regular Hadoop cluster. It has all the images, basically. So when you learn the stuff, you have to copy the data between these two clusters. So you have to, when you train, you have to copy the data to the deep learning cluster. Then you have the model, then you copy the model back to the storage part side. So this is not very convenient actually. So we try to avoid this kind of a copy, move data. So we want to move the algorithm to the data instead of move data to the algorithm. So we developed this CaffeOnSpark program. So it becomes part of this our ecosystem basically. We have all kinds of other machine learning libraries. So we have this Hive, Spark SQL, and now the CaffeOnSpark is another member of this Spark family basically. So on any given day, you can see that a lot of scientists inside Yahoo are using Spark, sometimes using Spark shells. I think that sometimes using MapReduce, but a lot of Spark jobs actually are CaffeOnSpark. You can see that we give two examples here. So it's a very popular application inside Yahoo. So for those who are familiar with Spark, so this is what you see when you run the CaffeOnSpark. It's basically a Spark job. So you will see all these, you can see all these progresses bars and all the stages, because it's basically a Spark job. Now for those who are very familiar with the Caffe side, so this is what you see. You can see the log. So these are the logs generated by the Caffe basically. So if you're familiar with both sides, you can look at both. If you're only interested in one of them, you can just look at either of them. So the command line actually pretty simple. It's just a Spark job, right? So we have basically if you want to submit a job, you do a Spark submit. Then there's you specify the number of executors, the class name, and so all the number of devices per process basically. Then you can give it a configuration file, give it a model. So this side is basically the Spark side, and if you go to the Caffe side, you see here's how we modified the original Caffe code, Caffe configuration file. So we added 2 lines basically. One is specify where the source is, and then what kind of a source this is. So in this example, this is the LMDB file, data set basically, and it is located in HDFS. So as I just mentioned, we support a couple of data formats. So one of them is LMDB, and this is the original Caffe format actually. So we support it because a lot of people, Caffe guys actually like this format, but we also introduced a new format called data frame. It's more like distributed, because LMDB is not distributed file system. So sometimes if you have a really big data set, like a Flickr data set, it's really big, you cannot actually use that LMDB, because so basically you end up with a single file, very big, very big file basically. So you can convert it between these two, but we support both of them. So data frame basically it's a table. So you have IDs in the example. You have IDs on the left hand side. You have IDs. You have label, and you have the images. Then you go through this training process. And then you get a model, and also you get the feature extraction step, and then you get the features. So it converts that the table on the left to the table on the right. So you get the feature number 1, feature number 2, and so on and so forth. So we provided the Caffe, the Scala API. So this is how you run it. If you have a Scala, if you want to run in Scala, this is how you run it. So basically, you prepare the context, and then you specify where the source is, and you call the training function, and it will just train model. And once you get a model, you can call the features, and you can extract the features. Then. So in this case, you can also concatenate the non-deep learning approach. So next, you can call the logistic regression in this case, and you can train a logistic regression on top of the Caffe. We also provide IPython notebook API, so that you can treat it as a Python. Basically Python. You can use Python to train this thing. So we can visualize the network, and we can train it, and Miller will give a demo. So I'm gonna just quickly overview this. So you can test it, and you can do a feature extraction. So there are multiple ways to deploy it. So first, you can do a single node deployment. And you can of course have a multi-node with Ethernet connection. And you can, for example, you can launch it on EC2, Amazon EC2. And internally at Yahoo, we use multiple node with InfiniBand because that's faster. So this is the scalable architecture. So you can have more nodes. You have lots of executors basically. You have added nodes, and each node could have multiple GPUs, and we can use all the GPUs or all the nodes to train the model. And that the connections, you can use the Ethernet, or you can use the InfiniBand, all kinds of connections. So that actually speed up the training quite a bit. So in one, we did a benchmark a long time back. So we tried, one GPU, two GPU, and four GPU, 8, 16, 32, and 64. Of course, you get a diminishing return because as you add more and more nodes and add more and more GPUs, what happens is you can have a lot of communication overhead. So in that case, you get a diminishing return. But in this particular example, we trained the ImageNet with the GoogleNet. We just I showed you earlier that the GoogleNet, and we get like about 16 speed up with 32 GPUs. So that was a very early result. We didn't actually optimize it, but if we optimize it, I think we can get more speed up. So that's the, I guess that's pretty much it I have. So next, Mildred will give you a demo on this.
So I'm going to give actually two demos. One is command line and another is IPython notebook. So this is EC2. So many people would have used EC2. The first thing that we do here is okay. So first, if you have used EC2, there's an AWS client. You can actually install your EC2 instances through the AWS client. This is command line, so I'm not going to get into the details of this. I already have an EC2 instance running, which has one master and two slaves. And once you have set this up, so we have actually this wiki which you can go to on GitHub for CaffeOnSpark, and from there on you can actually see all these instructions how to set up the EC2 instance. You can also see how to set up for Python, Yarn, your OS X, or your local installs in Ubuntu. Right. So we have all the things. We have GPU, CPU on InfiniBand, on Ethernet, on all the platforms. Okay, so once you have once you have spawned your EC2 instances, the next thing that you have to do is just SSH into those, and I'm going to do that. But before that, just trying to explain what we are going to do and what you will see exactly, so that you can correlate the two. So we basically specify a bunch of parameters here. So how many cores or how many CPUs do we want to assign to each of the workers? So we have two slaves and one master, as I said, and how many cores per workers and executors. And devices refers to how many GPUs. So this is one GPU which we are going to assign. And then I'm just going to do a Spark submit, and some of the details of Spark submit is to do with which is your master node. And this is standard Spark, so most of the people who know Spark already know this. These are the files. These are your solver files, so the network files which you need to ship, and the different configurations. So without actually, so I can actually discuss more of this, but let's get into the demo itself. I need to. Okay. So I'm going to SSH into the EC2 master first. You can't see it. Okay. And actually export some of the files and parameters. So these are all to do with your local paths, your settings, which are given in the wiki. And then I'm just going to specify the things which we discussed: how many cores per workers, how many GPUs, Spark worker instances, etc. So now that we have all of this set up, I'm just going to do this Spark submit. So this demo shows that from a command line, you can actually execute the whole network. So this is the master. So here you can see that the Spark job is launched. The whole system is running. And I'm going to explain how the whole network is going to look like. But you can actually see these details in the Spark tracker or the job tracker. So here you have the job tracker, and you can see that the instance has been launched and it's going on, and you can see the executor logs. These are the two slaves which I was talking about, and you can see the logs as to what's happening. So the whole network has been launched, the whole distributed CaffeOnSpark has been launched, and the different iterations are going on. So here you can see we are actually doing some 10,000 iterations on the MNIST handwritten recognition dataset. So you can see that these are going on. It's on the 900 one, and then if you refresh, you can see that it goes further. So I'm not going to. So it's 2,500 right now. So I'm going to actually cut short right now and then go into the IPython demo. So I'm going to stop this and run the IPython demo. So for IPython, what we need to do is launch IPython on the Spark shell and on our EC2 master, and after that, so this is the command. These are the same bunch of parameters which you are seeing in Spark submit, except that there are certain Python specific settings here. So I'm going to launch this, and sorry. So if you do not do export of the display, it's going to launch the IPython notebook on your shell itself. So I just have to export the display so that I can connect to it from a browser, and I can do all my deep learning through the browser. So here you can see that there is a particular URL on which this particular notebook is available. So how many people have used IPython notebook? Okay, cool. So now we can actually really look at the IPython notebook and do all our things through the browser. So I think this is the URL, I think. Okay, so here this particular, okay, so what I'm going to do here is I'm running the MNIST handwritten dataset. So this is a collection of around 70,000 handwritten grayscale images. And this IPython notebook is connected to my Spark cluster on EC2. And whatever I execute here on the browser, it's going to get executed in Spark. So it's pretty convenient. You can do all your programming through this particular browser interface, all your deep learning and your classical machine learning, everything. So the first thing that you do is, if everything goes right, you're going to actually import a bunch of utilities and certain modules for CaffeOnSpark. For CaffeOnSpark, actually we need to import only 3 modules. One is CaffeOnSpark, config, and data source, which is what June was talking about. And then you can load your dataset. My dataset is available already on the HDFS Spark cluster, and it is in Parquet format. So I can actually load that particular dataset just from my command line here, from the browser here, into a Python data frame. So this is very convenient. If you have access to any of your data in HDFS, you don't have to go into HDFS, copy the data here and there. You can just go to the IPython notebook and then load the data into a data frame, IPython data frame, or Python data frame. And you can see the data, so we can visualize the data. So by the way, some of the things that you see here is from the last one when I was running it. So whenever you see a star, it is executing actually all of these things here on the console. So it's executing on Spark. So this is the first 5 images in that particular data set. And here you can see that this is labeled. So you have these symbols, and the labels for those symbols in MNIST are 7, 2, 1, 0, and 4. And in Caffe, actually, you can define your whole network, the neural net, in a simple text file or proto text file. And that particular file, instead of showing that file, I can actually show you that particular file. I mean, what's there in that file through a visual diagram. So when you see a star, it runs in real time and actually displays this whole network. All right. So the basic idea here is that we are going to take all these data sets, so 60,000 training set images of grayscale, and pass it through a neural net. The neural net is going to extract features from that particular data set, is going to learn certain parameters, and once the learning is done, whenever we pass a symbol like this through the data set, unlabeled symbol like this through the neural net, hopefully it is going to recognize that particular symbol as number 4. So let's do that. This is how your network looks like. You have the data, which has 2 sets. One is your images and your labels. So images are these images that you saw, and the labels are these tag labels. So you pass it through the network. Here you have a convolution layer and a pooling layer. These are the details of the LNet network, which you can search on the web. I'm not going to get into the details of the neural net itself. So once all these 60,000 examples, so this I'm just showing 5, but there are 60,000 such examples, labeled examples. Once they have gone through the net, and it has been trained, whenever you pass a symbol like this, or any image, for every image, it is going to produce 10 specific scores or 10 probabilities. So the way to read those probabilities is this. What is the probability of this symbol being 0? What is the probability of this symbol being 1? What is the probability of this symbol being 2? And so on and so forth till 10. Right? And hopefully we will get a probability, we will select the highest probability, and hopefully the index corresponding to that particular probability will be number 4. So that should have the highest index, right? So let's do that. So for training, so we are going to do live training here. So for training, all you have to do is instantiate CaffeOnSpark object. Since you have already imported all the modules of CaffeOnSpark, so all you have to do is instantiate that object. So let's run that. And then you have to tell your solver file. The solver file basically is this file. This is a visual diagram, but basically it tells you where the neural net is, where the data set is, where the training set, where is the test set, etc. Right? So you give all that. You also specify where the training model should be generated. So once the neural net has learned everything, it has to capture that whole knowledge in a model, and that is the model which is depicted here. So you have to tell the path in HDFS where the model should be produced after training. So you give that. And then here I specify the connection is Ethernet and the cluster size is 2, which means there are 2 executors running on 2 slaves. I mean 1 executor on each slave. So I'm going to give that, and then I'm just going to start the training. All right. So while the training is going on, I just want to call out what's happening here is that there are 2 slaves, and there's 1 executor, which is a process in each of the slaves, and there's 1 GPU because we selected device as 1. There's 1, so we selected device as 1 here. So there is 1 GPU on each of those processes. And inside each of those GPUs, a complete neural net, which you have a neural net like this, runs. Complete neural net runs. Now, of course, you can see the details of all these trainings on the job tracker, on your Spark job tracker here. This is for the old job, but let's do it for the new one. So this is for the new one, which is running from IPython notebook, which we just now launched. And I think the training is going on, and as you can see, the iterations are happening. So what are these iterations? Let's look into that. So what happens in training is, first and foremost, you have these 60,000 examples of training set. Yarn, basically with the help of Yarn, first and foremost, Yarn takes care of spawning these executors automatically on your cluster. And that's where we use scheduling of Yarn. So you don't have to deal with all the scheduling, etc. And Spark will take care of partitioning all your data set, these 60,000 images, into let's say 30,000 each through RDDs. And these will run on each of the executors. So 30,000 on one executor, 30,000 on another executor. Now, what's happening during training is that you have a batch. So let's say take one executor and you have 30,000 images. You take 100 images at a time, pass it through a neural net. It's going to take each of these images and try to come up with those 10 scores. Of course, those won't be correct in the beginning because the net is not trained. And those scores, but we know actually the real data set. So we can calculate the difference. That difference in error is passed back and back propagated into this whole network automatically during this training process. And the weights in each of these networks is adjusted automatically. And that's what happens. So this is the network in which the weights will get adjusted. This is what is happening during training. So we'll take each of these batches of examples and keep passing it through, and the weights will get adjusted. Now the whole thing about CaffeOnSpark is this is not running on a single box. So as I said, this could be running on a cluster. So you have this whole network running on multiple GPUs, right? So you have, in this particular case, it's running on one GPU in one cluster, one node, and another GPU on another node. So whenever this is happening, whenever this training is happening, before the beginning of every iteration, you have to make sure that the corresponding layers, so your neural net is composed of multiple layers, layer 1, 2, 3 here. So each of the layers should have the same weights, and whenever the training is going on, it will change the weights, and you have to sync the weights between all the nodes. So whenever you have to sync the weights between all the nodes in a distributed setting, you have to actually exchange data, and that's why network bandwidth is utilized. That's why Ethernet is going to be slow, and that is the reason we use InfiniBand, which is pretty fast. So a lot of data is exchanged after every iteration, and we are running around 10,000 iterations here with batch size of 100 images at a time, right? So this is happening parallelly in the whole cluster, and there are multiple networks running, and each of them need to exchange gradients. So that's what happens during training, and so our training is done, and I can now run the test set. Test set is pretty small, that is 10,000 images without labels. Of course, we know the labels, but we are going to pretend that we don't know the labels. And then we are going to run the test set here because the network is already trained. Now we are just going to pass unlabeled set, and we'll see what it does. So overall, it says that the network succeeded with an overall accuracy of 99%. And let's see what it extracted. So what is training is basically whenever you are feeding in all these images, it's trying to extract certain patterns about this particular image. It is trying to understand specific patterns and trying to put that pattern into knowledge. And those are called features. So you have features like the shape of the images or whatever, right? So let's try to see extract some features itself. So you can extract some features using this CaffeOnSpark. And I have extracted three features rather, accuracy, IP1 and IP2. So these are intermediate features which you have on CaffeOnSpark, for MNIST. And here you can see the features have been extracted, and I get this particular array, IP1 and IP2. And these are intermediate features. And then I can show it much beautifully using pandas. So one of the things here which happens is whenever you do your deep learning in IPython notebook, you can use all the Python libraries to do all kinds of graphing and visualization and all those kind of things. And once you have that, you can actually take your intermediate data. So of course we have got our scores. So here what this says is that we had the labels for each of these images. So we have the first 5 images which I'm showing. And the predictions for those images were predicted as 7, 2, 1, 0, and 4. And this actually, if you want to expand this, I can show it later. This is this is an array of 10 numbers, and we actually chose the probability index corresponding to the highest probability, and that index was 7, and that is the prediction here which matches the label. And we have the second prediction 2 and 2, and so on and so forth. This is a very solved problem, and MNIST is a solved problem. That's the reason the accuracy is pretty high on these in this deep learning framework, right? Now, one of the key features is I extracted this final features, which are the labels, but you could have extracted certain intermediate features, which are for our use case. You can just see a bunch of features, abstract numbers. And what you can do here is one of the USPs of CaffeOnSpark is that you don't have to have, wherever your data resides, you do your deep learning there, you do your classical machine learning there. So basically, we have our data on our cluster in HDFS. We actually took that data and fed it into deep learning algorithms, and it produced a bunch of features and advanced features as well as end results. We can take certain advanced features from there. Instead of calculating the end result, we can take certain advanced features from there. And as in the Spark talks, Mohammed was mentioning, you can actually use logistic regression from MLlib, Spark itself, and use these intermediate features from deep learning and pass it to MLlib. So I'm just going to load MLlib here. And I'm just going to run a logistic regression. So what we have done here is logistic regression is going to produce the same set of 10 scores because we took some intermediate features instead of the end results and fed it into a logistic regression algorithm, which has nothing to do with deep learning. It's just simple classical classification algorithm. Right? And we run logistic regression here, and we see the predictions. And the predictions are again 7, 2, 1, and 0, and 4. So one of the key things here to take away is that you have your data, you have your deep learning, and you have your classical machine learning all happening in the same cluster through a single place and through a single program rather. And you can exchange data through each of those using simple data frames. Thanks.
Any questions?
Yeah, let's take some questions.
Spark has a similar effort called the SparkNet. How do you compare this one to the SparkNet?
Okay, you want to take that?
Sure. Yes, this is a very popular question. SparkNet is a project from two of our friends in the Berkeley PhD program. So what they did was embedded Caffe into the normal Spark architecture. So what they mean is they put the Caffe inside the executors. And what so all of the executors are independent on each other. They do not talk with each other. So as a result, they do whatever thing you learn from a small batch, they go back to the driver to do the coordinations. So instead, what we are doing here is have the executor talk with each other, because we believe there's so much data information need to be exchanged for the deep learning. So it's important to have very fast, and we do not want anything like the driver becomes the bottleneck. So that's why this thing was designed to be able to much better scale up.
Do you have the performance comparison?
I think we have not, we are not really trying to compete with each other. I think I'm sure, all is the best. Yeah, but I mean, that team is doing quite a good job. I think since we launched our thing, now they moved on to TensorFlow. That's good. Any other questions? Thank you all. Thanks.
Thank you everybody for attending the session today.